Hi class, in this part of Chapter 5 we're going to talk about light, and we talked a little bit about it already, the different ways that light interacts with matter, but now we want to talk more specifically about what light is and how we describe it, different colors and things like that. So what is light is the first part, and then we'll talk about the electromagnetic spectrum. So we'll find that light is not just what you see, red, green, blue, and so on, but there's a lot of different kinds of light that we don't see. So we'll talk about those. So we can, when we talk about light, we can talk about light as behaving in two different ways that seem very different, very sort of distinct. But light acts in both ways, depending on how you're kind of observing it. So when you're thinking about light as just traveling from one point to another, say from a star to your eye, to your telescope or something, we can think about light as acting like a wave. But if you think about light as interacting with matter, when it gets absorbed or emitted, it's better to think about light as a photon, a particle of light, a particle of energy. And both ways are necessary to describe fully how light interacts and how light behaves. So particles as well as waves. It seems kind of strange, but it's true. So we'll talk about the differences. So what is a wave? Just in general, what is a wave? If you think about throwing a pebble into a pond, you know that when you throw that pebble into a pond, and we'll see a little simulation of this, the water kind of forms these little ripples that travel outward away from where the pebble hit. And the ripples are places where the water gets a little bit higher than normal or gets a little bit lower than normal. So the place where the water is a little bit higher than normal is called a peak, and the place where the water is a little bit lower than normal is called a trough. And so when you throw this pebble in the water, you see these series of ripples traveling outward from the splash, from the point where the pebble hit. And those little ripples are series or sequences of peaks and troughs that travel outward. And then if you have like a little something floating on the water, like a feather, you would see that that little feather just bobs up and down as these peaks and these troughs pass by it. And then the distance between adjacent peaks or adjacent troughs is something we call the wavelength. So the wavelength of a wave is the distance from one peak to the next, or from one trough to the next. And the waves travel away from that point where they're created at a certain speed, whatever the wave speed is. And then we can also think about something called the frequency of a wave. And the frequency is if you were sitting at a particular point, like where this leaf is located, and you just watch the wave go by, the wave would go by a certain number of wavelengths every second. That's the frequency. Or how many times does this feather go up and down every second? That's the frequency of the wave. So we'll look at those terms again in a moment. So here's a kind of a visual picture, sort of a cross section. If we kind of looked at the water, if you imagine this blue line being the water level at a given point, or before the wave comes along, let's say, and then when the wave comes along, there's a certain place where the water is higher, a certain place where the water is lower than normal, higher than normal, lower than normal, and so on. And this might be the location of that feather. And right now the feather is kind of lower than normal. And if this wave is traveling to the right, eventually this point where the water is higher is going to get to the feather, and it's going to raise the feather up. And so as the wave travels to the right, this feather gets pushed up and down as this wave travels past it. The wave itself isn't carrying water with it. The wave is just simply making the water rise up and rise down. So the feather pretty much stays in one position. It just goes up and down as this wave travels by. And so the wavelength, again, is the distance between adjacent peaks or adjacent troughs from there to there. And the frequency, again, is the number of wavelengths that pass by every second. Or thinking about the feather bobbing up and down, it's the number of times the feather goes up and down every second. So if you're looking at one point in space, how many wavelengths every second pass by? That's the frequency. So if you were to multiply the wavelength, the length of a wave, times the frequency, so this is the distance in meters from one peak to another, times frequency, and frequency is waves per second. So this wavelength is like distance per wave, and frequency is waves per second. The overall thing that you have when you multiply this is distance per second, and that's a velocity, that's a wave speed. So wave speed is given by wavelength times frequency. Frequency is in meters, or distance is, wavelength is in meters, sorry. Frequency is in times per second or waves per second, something per second. And so the quantity meters per second is a speed. So in terms of an electromagnetic wave, a light wave, what a light wave is it's not vibrating water or something like that, but it's vibrating what's called the electric field. So we have talked about that a little bit before. There's this thing called the electric and the magnetic field, and they're what light waves are made of. And those are the things that are vibrating. If you stood at a certain point in space, like right here, you would feel an electric field getting bigger, pointing upward, and then getting smaller, pointing upward, getting bigger, pointing downward, getting smaller, pointing downward, and so on. So in this picture at the moment, it shows a bunch of electrons. It's a kind of a sort of a deceiving picture, so it makes it sort of, might make you think that a light wave is a vibrating chain of electrons. That's not what's going on here. What's happening here is they're imagining that if you did have a bunch of electrons just kind of sitting along this dotted line, when this wave passes, as this wave is passing by, the electric field pushes the electrons one way or the other. And in this picture, these electrons have been pushed upward, while these electrons have been pushed downward, and so have these. So the electric field pushes the electrons either up or down, up and down, up and down, as the wave passes by. This isn't a great picture. Again, you got to try to remember that we're not talking about electrons vibrating around all the time. But if there were electrons present when an electromagnetic wave passed by, that electric field would push those electrons back and forth, back and forth, back and forth as the wave passes by. So light interacts with charged particles through this electric and magnetic field, and the changing electric and magnetic field as the wave passes by can push the electrons or any charged particle back and forth and back and forth and back and forth. So an electromagnetic wave, a light wave, is basically an oscillating, a changing electric field along with a changing magnetic field that travels in a particular direction at the speed of light. So there's a couple good simulations that I want to show you. We've seen some of these before. There's again this phet.colorado.edu site, and there's a bunch of physics simulations as well as others. The one we're going to look at in particular is the radio wave simulation, and then we'll look at some of the interactive figures on Master in Astronomy or in our course's D2L site. So if you use your web browser and go to this link, this phet.colorado.edu site, there's one called Radio Waves. This is a Java applet, so it might not necessarily open in your browser, but you might open it in a separate window. And so we've got that open here. And so what this shows is it shows a kind of like a flagpole. It's more like an antenna, a radio wave antenna, a radio station that broadcasts some radio station has an antenna somewhere. And so imagine that this isn't the antenna. And in that antenna, like in any piece of metal, there are electrons. And to broadcast your radio station, you make those electrons vibrate up and down, up and down, up and down. And it turns out that if you take a charged particle like an electron and you make it vibrate, it gives off light. It gives off, in this case, radio waves, depending on the frequency of that electron. And so what we're going to do here is we're going to make this electron vibrate, and we're going to see it giving off an oscillating electric field. And that electric field is going to travel outward at the speed of light. And eventually it's going to encounter this electron in this antenna. So this is another piece of metal that has a bunch of electrons in it, as all pieces of metal do. And these electrons in here are going to feel that electric field. They're going to get pushed around by the electric field. They're going to start vibrating at the same frequency that this electric field is vibrating at that we've created. So this would be your radio station's antenna, the transmitting antenna. This would be the receiving antenna. And the receiving antenna then just feels that electric field pushing the electrons around. And then there's some electric circuitry connected to the antenna that senses the movement of those electrons and then plays that, amplifies it, plays it to a speaker, and then you can hear the radio station. So what we can do is we can just manually make this electron move up and down. And I'll do this. Oops, let me play it. Okay, so manually move it up and down. And as I move it up and down, I'm creating this vibrating electric field, the red arrows, the red wave. And you can see that electron over on the right is now wiggling up and down in response to that electric field hitting it, in a sense. And it's not moving a lot, because the wave gets weaker as it moves further away from the source. But I'm creating an electric field wave, and the electron over on the right is feeling it, is responding to it, is getting pushed around by it, back and forth. So that's how a radio transmitter works. There's a radio antenna where there's an electric circuit that forces the electrons to move back and forth. Those electrons that move back and forth create an electric field that oscillates, and then it travels away from the source at the speed of light. And then if there's any other charges in the way of that wave, those charges will get pushed around. So this guy gets pushed up and down, not very much, but enough that we could detect it, that we could sense it electronically, maybe amplify the signal, send it to a speaker, and hear the radio station. So that's basically how a radio station works. And that's really how almost really any light source works. Light is created by oscillating or vibrating charged particles, and then that light wave travels outward and it can interact with other charged particles. So and there's other things you can play with on here. You could actually do a manual or a kind of an automatic sort of oscillation. So here we've got the electron in the antenna vibrating more slowly. We get a nice smooth wave that's created, and you can see how the response is kind of more pronounced over here now. The frequency isn't quite so crazy as what I had before when I was making it vibrate, but you can clearly see now that the vibration of this guy is forcing the vibration of this guy to occur. And there's this nice wave that's traveling along to the right and to the left, in all directions away from the source. So some other interactive figures from your book is here's just showing the person dropping the pebble into the water. They throw the pebble in the water, it hits the water, and there's a feather over there, and the feather bobs up and down as the wave passes by. And so the feather stays in one position, but it bobs up and down. And that indicates that the wave is not moving the water outward, away from that point where the rock hit, but rather the wave is just a disturbance that travels along the surface of the water. And it doesn't actually move the water outward, it just makes the water vibrate up and down. So that's that little simulation. And you can try this at home when you find a pond somewhere, just toss a little pebble in there and you can see the ripples of water travel outward. This one shows, again, that same view, that same situation, but kind of from the side view. Here's your little feather floating in the water, and the feather is not moving to the right or to the left. Neither is the water. And it might look like it is. It might look like this water is traveling to the right, but it's really not the water that's traveling to the right. It's the disturbance that's traveling to the right. The water is simply just going up and down. If the water were traveling to the right, then the feather would be moving with the water as it travels to the right. So the wavelength is the distance between the peaks or the troughs, and the frequency is the amount of time between vibrations of the feather, for example. And you can see that's given by the blinking of this light. The faster this light blinks, the higher the frequency. And then light waves are the same, except you'd have a vibrating electric and magnetic field. As at this point in space, if this were an electron and this were an electromagnetic wave, the electron would get pushed up and down as the electric field wave comes by. Other things that you might think about is something called the amplitude of the wave. The amplitude is how big the wave is, in a sense. How far from what you might call equilibrium does the feather get pushed up or down. And so if you were to draw the wave, maximums and minimums, and then draw it kind of as it's shifted, this point right here would at some point be at a maximum, and then a later time be at a minimum. Half that distance between a peak and a trough, the height of the peak and the depth of the trough, half that distance is called the amplitude. It gives you a sense of how big the wave is compared to what we call equilibrium, where the feather in this example would be if there were no wave at all. If we compare light and water waves, water waves move at a much slower speed, right? About 1 meter per second, who knows? There's a variety of speeds. Electromagnetic waves, light waves, travel at a much higher speed, 300,000 kilometers per second. So that's light is very, very fast. And then the other simulation here, the interactive figure, it just shows you some things, and we'll look at this again later, but there's different parts of the electromagnetic spectrum. Light isn't just the visible light that you see. So visible light, if we click on that, obviously comes from stars, our sun, for example. We can see it comes from light bulbs. It's all the colors between red and purple that you can see with your eye. But there's a lot more electromagnetic radiation out there that we don't see with our eye, but we know it exists. Ultraviolet, for example, is given off by our sun as well, and that's what gives you suntans and sunburns. Or if you sit in a tanning bed, those light bulbs have ultraviolet light shining coming out of them, and they give you a tan. So you have to wear special glasses in there so you don't burn your eyes. So that's ultraviolet. X-rays come from certain sources. There's stars when they explode. In a supernova explosion, they give off massive X-rays, massive amounts of X-rays. You can produce X-rays in the laboratory and send them through your hand to see your bones, or to see more dense material like your bones. So we can make them in the laboratory, X-rays, or we can produce them out in nature. And then gamma rays are just even more high energy light. And so going from visible to ultraviolet to X-rays and gamma rays, that's an increase in energy, a decrease in wavelength. See how the distance between the waves is getting shorter and shorter. So gamma rays are also produced in the deaths of stars, or perhaps when two massive objects, like we'll talk about black holes and neutron stars and things like that, when they collide, they might produce gamma rays. We can also produce gamma rays from radioactive elements. When radioactive elements decay, some of them can give off gamma rays. Gamma radiation is radioactive radiation, in a sense. So those are the really high energy rays of light, or waves of light, if you will. On the other side, again, there's visible, but much longer wavelength is infrared. And infrared light is given off by you. You are an infrared light bulb. You give off infrared light. If you went into a completely dark room, no visible light whatsoever, and you opened your eyes, it was completely dark. But if you had then a camera that was sensitive to infrared radiation, you would be able to see yourself. And this is kind of an image of what you might see. Certain parts of your body might be warmer than other parts, and the warmth, the temperature of your body tells you the kind of light that you're giving off. And so this is what we call a false color image. Your face is not actually red, but it just indicates that there's a particular sort of brightness of a particular wavelength coming off of your face. In this image, what they've done is they've used red to color the warmer areas and blue to color the cooler areas. And so there's certain areas on your body that are cooler than other areas, and so they're giving off different wavelengths of infrared radiation. And then there's the radio part of the spectrum, which includes the microwave part of the spectrum. There's a big overlap in here, radio waves and microwaves. They're very similar, but they're even longer wavelength waves. Microwaves are given off by your microwave oven. So these are longer wavelength, they're lower energy, and so you might think, well, how can things get so hot in a microwave oven if there's not a lot of energy there? You know, if there's more energy in visible light than there is in microwave light, why can't I cook my food with visible light? Well, it's because of the response of water molecules to a particular wavelength of microwaves that you use in a microwave oven. It causes them to vibrate more vigorously. They can absorb that energy, and we talked about previously how if you get little molecules or atoms to move around more rapidly, that's really an increase in temperature. And so a particular wavelength of microwave radiation is absorbed by water molecules, causing them to vibrate more vigorously. And that more vigorous vibration is manifest in a higher temperature. And so the food gets warmer and hotter, and then it cooks. And there's also cosmic sources of microwaves. There's something called the cosmic microwave background radiation. We'll talk about in a later chapter. There's microwave radiation coming from all parts of the universe, from all directions. And we can measure it and see differences in what it looks like in different places. And it gives us a good sense of what the universe looked like long, long time ago. And it's very strong evidence of the Big Bang, the idea that the universe was created out of nothing, basically, a point that exploded somehow. So we'll talk about that later. Radio waves, then, are emitted by radio stations, radio towers. They're also emitted by other galactic or extragalactic sources and various processes that occur in galaxies that we'll talk about eventually. So all these different wavelengths of light, very short wavelength gamma rays to very long wavelength radio waves, they can all be produced here on Earth by various sources. They can also all be produced in space through various sources. So as an astronomer, you need to be able to measure these things. You need to be able to detect these things. And our eyes can only detect visible light. So we need all kinds of different cameras and telescopes and things like that to detect these different types of radiation, electromagnetic light, electromagnetic radiation. So this is another little picture that shows certain wavelengths And if you remember that we talked about wavelength times frequency is the speed of light. So as this wavelength gets smaller, this frequency gets bigger in order for these two numbers to multiply to get the speed of light, which is a constant, 3 times 10 to the 8 meters per second. So as the wavelength gets smaller from this one to this one to this one, the frequency gets bigger, 30 gigahertz, 60 gigahertz, 120 gigahertz, and so on. So then we also talked about light, the fact that it can act like a photon, a particle. And this is really important when you talk about light being absorbed or emitted by something. It turns out that when matter absorbs light, it absorbs it in sort of chunks, in sort of pieces. And those pieces are what we call photons, sort of chunks of energy. We still, even though the photon isn't a wave, the photon isn't necessarily something that's spread out like a wave, we still refer to it as having a wavelength and a frequency. It's related to the photon's energy. So we'll look at that. So again, this is a kind of a more symbolic way to write that equation. We talked about wavelength times frequency equals the speed of light. So this is the Greek letter lambda. That's what we typically use for wavelength. Multiplied by the frequency, f. You get c, the speed of light, 3 times 10 to the 8 meters per second. And it turns out then, this is something that Albert Einstein won the Nobel Prize on. He showed by something called the photoelectric effect. He explained this thing called the photoelectric effect. And to explain it, he suggested that light is absorbed as chunks of energy, and those chunks of energy have energy related to the frequency of the wave that you might have used. So if you shine, let's say, red light on something, that red light has a certain wavelength, therefore has a certain frequency. And if you take that frequency and multiply by this thing called Planck's constant, which is this number here, you get the energy of the photon. And Albert Einstein showed that this explains this thing called the photoelectric effect. So this Planck's constant was kind of developed through some other analysis, a different experiment that a fellow by the name of Max Planck talked about and tried to solve, tried to understand. And we'll talk a little bit about that later. But Albert Einstein said, oh, let's take this thing and let's suppose that the energy of a photon is this Planck's constant times the frequency. And it turns out that if you do that, it really accurately explains the results of this thing called the photoelectric effect. And Albert Einstein won the Nobel Prize in the 1920s for the explanation of the photoelectric effect, for introducing the idea of particles of light, photons of light. Right? So waves have wavelength, have frequency, and have speeds, but these particles of light have energy, and we can also refer to those particles as having a certain frequency and a certain wavelength. But it isn't like the particle is vibrating or anything. So the particle is not like the wave. The particle is just like a chunk of energy. But we can still kind of relate its energy to a frequency of a wave that we might be shining on something, so that the energy from that wave can get absorbed in the form of photons, particles of energy. So one last thing we can talk about is polarization. We said that light travels, or light is an oscillating electric and magnetic field. And if you think about light traveling to the right, this electric field vibrates up and down as the light travels to the right. So if this is the speed of the light, this is the velocity direction, the direction of the velocity of light, light's traveling to the right, the electric field is kind of vibrating up and down and up and down. Well, if the direction of this electric field vibration is sort of always in the same sense, right, we say that light is polarized. In other words, literally, if the electric field is going up and down in the plane of this screen that you're looking at, then we say that light is polarized in, the direction of polarization is sort of vertical, up and down. If we look at this, let's look at this view. If we were looking in this direction toward the light as it's coming at us, and so if we drew a kind of a dot to represent the light coming right at us, like a beam of light coming right at us, all right? So this is a beam of light coming right at us. If the electric field is vibrating up and down like this, so the electric field might be vibrating up and down like that, that's polarization. That's polarized light. The electric field is vibrating in a particular plane. That's what you might call vertical polarization. But you could have it situated in a different way. If the electric field is vibrating back and forth like this, you'd call that horizontal polarization. But the polarization could be in any direction, any angle. So whatever direction the electric field is vibrating, if it is vibrating in a particular direction and not just kind of randomly, we say that that light is polarized. And so light coming out of typical light bulbs and stuff is really unpolarized. The electric field kind of vibrates sort of randomly in various directions. As time goes on, there isn't a particular plane of polarization. But if you wear polarized sunglasses, what happens with those sunglasses is the light comes into them, and the sunglasses themselves cause the light then that goes into your eye to be polarized. All right? Or another way to think about it is it can block light, the electric field that's vibrating in a particular direction. So if you wear sunglasses that have what's called like a vertical polarization to them, they will only let through light that is vibrating kind of in a vertical sense. And what that does is it actually kind of helps block certain reflections. And you might have noticed this if you wear polarized sunglasses, there's a lot of reflected light off of like shiny surfaces on the road or glares off of other cars and stuff like that get blocked. Because reflected light takes on a certain polarization, it turns out. So it says polarized sunglasses block light that reflects off of horizontal surfaces. So that's something we're not going to quite understand why that's true, but if light comes down from, let's say, the sun or streetlights and hits a shiny surface of the road, maybe that's wet, it bounces off the road and it comes back at you. So here's the road, and here's light coming down with kind of random polarization. As it reflects off the road and comes out up towards your eyes, this light that's coming up towards your eyes is more horizontally polarized because it reflected off this horizontal shiny surface. And so you don't want to see that light reflecting off of this shiny surface of the road. You'd rather see the light coming from the cars ahead and so on. So your sunglasses can block the reflected light. Not all of it, but a good enough amount that it helps you see a little bit better. So here's another picture from your book of the electromagnetic spectrum. This just could make some comparisons between wavelengths of the various types of electromagnetic radiation and objects that you might know something about. So the really, really short wavelength gamma rays, the wavelengths are really small, and these are numbers 10 to the minus 12 meters, 10 to the minus 10 meters, 10 to the minus 8 meters. And these are things that have similar sizes. A protein molecule is similar. Hydrogen atom is similar to this size. A bacteria is 10 to the minus 6 roughly in size. An animal cell, a pinhead, here a baseball. So here we're in the radio wave part of the spectrum, and we've got wavelengths that are a few centimeters, a few meters even. And so a baseball is as big as the wavelength of some short wavelength radio waves or long wavelength microwaves. The really long wavelength radio waves can be as big as a football field, and so on. This line shows you the frequencies. So frequency goes up in this direction as wavelength is getting smaller, frequency is getting bigger. And then this shows you the energy. Energy increases in this direction for for higher frequency, shorter wavelength. Energy gets bigger and bigger and bigger. And this down here shows you some sources on the Earth of these different types of radiation, and this shows you cosmic sources of these different types of radiation. So this is a good figure to kind of just look at and try to look at all the different levels of it and try to get a good understanding of the different parts of the electromagnetic spectrum and their sources and how the wavelength, frequency, and energy are all related to each other. So, quick question, the higher the photon energy, what happens? Does a higher photon energy mean that it has a longer wavelength, shorter wavelength, or that it doesn't depend on wavelength? So we wrote down before this equation that said energy is equal to h times frequency. If I can write this, h times f. We had that. And so that by itself makes it look like energy doesn't depend on wavelength because there's no wavelength in here. There's just frequency. But remember that wavelength times frequency gives you the speed of light, and the speed of light is a constant. That's just a number. And so if the frequency changes, the wavelength has to change as well. So really, you could take this thing and you could say, let's solve for frequency, f. Let's divide that by wavelength, c divided by lambda. So frequency is the speed of light divided by wavelength. And then you could plug in for frequency up here that energy then is h times frequency, but frequency is the speed of light divided by wavelength. And so this shows you that energy does depend on frequency, but it does depend on wavelength as well. So the higher the energy to make energy bigger, because wavelength is in the bottom, we have to make wavelength smaller. So a smaller thing in the bottom is going to make the whole fraction bigger. And so a higher energy photon should be a shorter wavelength. So what we talked about then is that light can behave like a particle or a wave. And again, generally, you want to think about this in terms of whether the light is just simply traveling through space from one point to another, or whether it's being absorbed and emitted. So it's best to think of light as a wave when it's just traveling, or as a particle, photon, when it's being absorbed or emitted. And when we think about the light wave, we think about an electromagnetic wave, an electric and magnetic field that's oscillating, it's vibrating. And then with the electromagnetic spectrum, our eyes cannot see much of it, only the visible part, which is a very, very small part of all the different types of electromagnetic energy, electromagnetic waves that are out there, light waves in general. And so the visible part that we can see is very, very small. We need other cameras, telescopes, and so on to see everything else. So that's all for this part. In the next part, we'll be looking a little bit more closely at light and how we learn some information about things out in space from the light that things give off or absorb or emit, and so on.